questions and comments. And if you do have a question or comment, make sure you draw my attention. If you just raise your hand, chances are I may not even see that you're raising my hand. So your hand. So speak up or draw my attention some other way. So let's talk about multi-threading. Why should we program multi-threaded applications? Now, when it comes to a server point of view, it's kind of clear why we would need multi-threading. Servers obviously would have to support multiple users, so multi-threading is kind of obvious. But if you're creating an application, why would you create multiple threads? Any reasons? Utilization of what? Hardware. But why I care? I don't care about the hardware utilization. Why should I care about it? What was that? Yeah, why do I care there's multi-core processors? I don't care about it. That's correct. I want to make my application responsive, right? So users, when they use the application, you want to make sure you respond. What is responsiveness, by the way? It is actually a very interesting world we live in. Let's say you call a phone for a service, and they say, please wait. What do? Hang up, right? You're not patient enough. But then they say, please wait, your call is important to us. Now you're waiting. And then they play a music for you, right? Or every few minutes there's something playing on. Now you're kind of hanging on to it. In other words, it's not about giving a response right away, but it's about being responsive. There's a very big difference between the two, right? Giving a response is you give the answer. Being responsive, like when I go to a store, by the way, and I walk in and nobody cares, they don't make an eye contact, I get irritated, I leave. But instead they look at me and say, oh, we'll be with you right back. I can wait there for 15 minutes because they acknowledge the presence that I came in there, right? So responsiveness simply means that your application responds to the users. One of the reasons is, not only do the users want to get results from the application, users often wonder, did the application just fail? Is it hanging? So they want some kind of a feedback that something is going on, and they would eventually get a response back. So let's talk about what makes things really hard in terms of getting responses back. Let's look at an example to begin with. This is a fairly simple example, but nevertheless, I hope it will help us to understand what the problem is. So I have a little application, no code really, much at all. I just dropped a Windows form, and I have a button click. That's all I have. Let's go ahead and run this little example. It says there's a ticker symbol, enter a ticker symbol, click on a display, not implemented yet. Fair enough? So it says that I can click on the display. Ideally, I want to see what's the stock price for Microsoft today, right? Anybody knows what's the stock price for Microsoft today? $31? We'll find out. Okay, so that's what we want to find out, right? So how do I implement this? So I have a little piece of code. We'll get to that code eventually. No rush to get to the price code right away. So I'm going to say over here, double value, of course, we'll call it as price equals. And I'm going to go to Yahoo Finance, which is just a little class I have. It's got a get price method. I'm going to call the get price method. And what am I interested in finding at this point? Well, obviously, I want to get the price for the ticker symbol we have on our hand. Where is the ticker symbol? I can say ticker symbol dot, I can get the value of the text from the text box, right, which is MSFT. So that gives me the price. And now that I have the price on my hand, what's the next thing I want to do? Oh, very simple. I will simply ask him to display the price, right? So string.format, and then we will tell him that I want to display basically the price over here. So we'll put a little dollar symbol, the price value that I want to put, and then we'll call it price. So that should be a fairly simple code, isn't it? So let's go ahead and run this and see if it's going to work. So as soon as I run it, it tells me go ahead and click on it. I click on the display, and I'm moving, by the way. I'm actually moving the window. And you can see that it doesn't respond anymore, right? And in fact, it says over here, not responding. How nice, right? That's the response we got, which is even worrisome, right? Now you're going to go to the Explorer and start killing it because it's obviously not responding. Well, what's really happening, though? What's really happening is I have gone to the web to look for the price right now. And of course, depending on the internet connection that I have here, that may take a little while, right, to respond. In fact, it's taking a lot while because of the wireless connection. Get off the wireless, please, right, so that this can work. So the point really is that can take quite a while to respond. What do we do, right? So you don't want to leave an application in this kind of state as the users are trying to interact with the application. You want them to be able to move the application around. You want to at least have them kill the application in a more graceful manner while this is happening. $33.31. See, it's even changed the price while we're waiting for it. You said $31, right? So the point is that you want this to be responsive. You don't want this to be stuck like that, right? Of course, while this application is not doing anything useful, I'm able to click on it. I'm able to move this around so you can see that it is responsive now. But the minute I click on display, it's no longer responsive. We are stuck again. So obviously, we want to fix it. Then the question is, how do we fix it? So the immediate answer we have is multi-threading. Create a thread and let things run on a separate thread. Oftentimes, unfortunately, that is easy said than done, because before you create a thread, you have one problem. The minute you create many threads, you have many problems now, right? So how do you deal with that kind of code? How do you manage that? So we're going to start by going back to the days we could create a thread and we could use it. But there are some very critical problems we have to handle, by the way. The first problem is creating a thread is the easiest thing we can do. But the minute we create a thread, we got to manage it. How do you tame this thread? And when thread is running, you got multiple threads running. What happens if these multiple threads are trying to change the data at the same time? We got issues with concurrency, race conditions, multiple things trying to collide on the same object. We got to deal with all those issues. How do we deal with it? So in order to work through all of those issues, we definitely want to make sure we protect the data that we try to change simultaneously. Well, but there's one other problem though. Anytime you do synchronization, there is an overhead to synchronization. And the minute you start synchronizing, by the way, synchronizing simply means you're going to pay a cost for synchronization even if there are no other threads running. So this is like if you are really a good disciplined driver, you could be driving home in the middle of the night and there's a red light and you stop at the red light very loyally. Even though there's no other intelligent human being on the street at the time, you still stop at the red light only to wait for the green and you move forward, right? And the day that you're kind of tempted not to stop is when there's a cop waiting in the corner. So the point really is that you will expend the price to do this. So what do they typically do? So to make this, solve this problem, what they typically do is graphical user interfaces normally, right, most of the time are single-threaded. So as a result, in most frameworks, including the Windows WPF, the Windows controls are not thread safe. This is by design, by the way, that is not thread safe. And because it's not thread safe, bad things can happen if you try to access the controls from multiple threads. Now, what could be the bad thing that can happen? If you are very lucky, your program will crash on your machine. If you're not very lucky, it'll wait for that important demo that you make, and then it'll crash at that opportune moment, right? Making a fool of everybody in the room. So that's how it can be misbehaving, and you got to be very careful about, accessing this from multiple threads. So what can you do about it? Well, we got to make sure you're on the right thread. That's one problem you have to handle, certainly, right? So getting back to this, we want to make the code responsive. The hard way to make the code responsive would be to, first of all, create a thread over here. Well, that is, like I said, easy said than done. So we could say thread, and what is this thread, by the way? The thread is an object we're going to use from the system threading, and I'm going to say new thread over here. So new thread, and fortunately it can take a nice delegate. So we can say thread. We can call this as a thread I want to start, and then we could say this is going to be the delegate I'm going to create. So the delegate basically in this case is going to do the real work. So what does it do? It says, I'm going to go talk to this object, Yahoo object, and then I'm going to update this price for you. So I'm going to go ahead and put that here within this. And of course, once I'm done with this, I'm just simply going to start the thread itself. So I don't really need to save this reference in this particular case. Well, this is really treading on dangerous grounds at this point. So I kind of put it into a separate thread, and I'm running it, and I click on the display. And if I'm very lucky, by the way, it would crash. Today's my lucky day. So notice it crashed right away. But usually I'm not that lucky, right? It crashes in unpredictable moments. Why did it crash? And the reason why it complained is that in this code, right here, I'm saying ticker symbol.text. So in this new thread I created, I touched the control and it said, how dare you control from this It even messes with my microphone, as you can see, right? So how dare you touch with this, and it tells me that I'm not supposed to go touch this other control from here. So what can I do to avoid that problem? Well, I'm going to say var ticker equals, and I'm going to say ticker symbol dot text. So I put it into a local variable, and then I'm going to go ahead and use that ticker right here to solve that particular problem, right? So in other words, I created a local variable in this context, and then of course because of the ability to use anonymous functions delegates here, that becomes lexical scoping on the stack. So I'm not messing with the shared variable, definitely not with the control variable. That's only half the problem though. The other half of the problem is now it's going to wait until the response comes back. It's going to crash. And why? Because I'm talking to the label here. I can't talk to it directly, right? So I'm going to say dispatcher over here and then call the invoke method on the dispatcher. And on the invoke method, I'm going to give him a delegate at this point. And in the delegate, I'm going to say, right here within this, let's do price label dot content. So I can do the rest of the code I was doing right here within that delegate code itself. So I could do that. So I'm going to just move this code right inside of this to say, that's when I want to update this within this particular context. So what does this do? Now I'm saying, hey, go in this other thread, access this local variable, go to Yahoo and get the price. When you're done, by the way, switch over to the UI thread using the invoke method, and the UI thread will go update the content, and then you can continue with this other thread, and of course the other thread would be over, and so we could run this and say, oh, I want to put this on as a different thread. So I'm running this now. Notice the nice thing is the application is responsive now. I'm able to move it around. It's still going to take time to get the response from the server and display it, but at least the application is responsive. Now, of course, because I took care of thread safety, right? But when you're writing code, you have to constantly watch where you are and say, am I in the right thread? Am I in the wrong thread? Am I in the UI thread? So notice the number of things you have to deal with. And when you have more things to deal with, what happens? That's more effort for us to put. So our productivity is low in writing the code. That's more opportunity for us to introduce bugs in code. That means the maintenance cost is going to be high. And even if you are the smartest programmer in the room, you write the code and you make sure everything works fine. And when you leave the room, you tell the people, it all works, by the way, and don't touch the code. Right? And that's not going to be fun developing software, right? Because other people won't be able to touch the code and evolve it, because anytime somebody touches code, it potentially is broken, and we got to put the effort to go back and fix it. So it's got to be a lot simpler than this. So there are too many things that go wrong in this particular case. We got to fix it. So the application was responsive. The application gave the same result as before, but the code is, and this is a very simple case already, right? And even in the simplest of case we can look at, we already have complexities already creeped in. So what can we do? So there are several challenges to multi-threading. One of the challenges is that you don't want threads to compete with each other and collide on variables. Synchronization becomes an issue. In this case, we didn't have to deal with it as much. The second problem we have to deal with is to make sure the threads are controlled properly. And the third thing we have to deal with is that we have to make sure that the things run in the proper threading context. We already solved that problem in this example. We put it in the right context to run it. But we already have another problem on hand as well. We said new thread, by the way, and that is something we should not do anymore. This was a bright idea back in 2001 when C# was introduced, because we didn't know better. And we started creating threads just like that. But over the time we realized creating threads like that is not a smart thing to do, because threads do take resource. And the more threads we create like that, we are going to have problems in memory consumption, performance, a lot of other things. So it's a much smarter approach to use a pool of threads and schedule tasks on the thread pool rather than creating threads over and over. So how do we really do that? So we want to use a thread pool rather than creating these arbitrary threads. So to do this, what we're going to do in this example is change the code just a little bit one more time. So rather than creating this new thread, there is a little thing called task that was introduced in .NET, and task is a pretty decent class. A task represents, as you would imagine, a little operation or task you want to execute, and the task by default can run in a pool of threads. You can control this to a certain extent, but it runs in a pool of thread. So as a result, as you create multiple tasks, it's going to run on a thread pool, so it's a lot more civilized and resourceful than just creating threads ourselves. So what am I going to do here? I'm going to create a new task over here, but there are different types of tasks, by the way. At the very primitive level, a task doesn't return anything and just runs stuff. But we also have a generic type of task which can return a result after it executes, and that is a lot more powerful to use. In this case, I'm saying I want a task that's going to return a value for me, a double value. So I'm creating an instance of task over here, and it can take an object of a function if I wanted to, and I can ask him to go run something and return a result for me. So in this case, I'm going to give him a lambda expression to run, and he's going to give me the result of this particular task. And of course, he needs a ticker, which is available in the scope over here as a lexical scoping, and I'm going to use that one. So what does this do? It gives me a task on my hand, so I'm going to say task equals, and then set that into the task itself. So I just saved it away in the task over here, and that's what you're seeing at this point. So now that I have a task that I've created, what's the next thing I want to do? Well, obviously I want to go run this task, but once I run the task, I've covered this part of sending the request, but what about the response? I want to get the response and process it, isn't it? Well, I want to get the response and process it, but how do I do that? I want to get the result from this guy, and then I have to go do some work, but unfortunately, where can I do it? Well, obviously, it gave me a task, and if I wait on the task right now, our application will no longer be responsive, right? So it's kind of like saying, I create a thread, that thread is doing the job, and while the thread is doing the job, I will wait on it. That doesn't make any sense, right? So while the thread is doing the job, you want to go respond to the user interaction, and then of course, when the thread is over, you want to come back and do your work. So what can you do for that? Well, you got to listen to the event that it is finished. So I'm going to say task over here, and continue with. And continue with is going to be called when the task is completed. So in this case, I'm going to say, what do I do with this? I'm going to say completed task. And now that I have a completed task on my hand, I can say display result. And completed task is going to give me the result itself, and I can use that result to display the result of this computation. Now, I don't know what display result is. We'll come back to that in a minute. And then I have to say, start the task itself so it can run in a separate thread. Now, how is this different from what we did before? The only difference at this point is, rather than we creating a thread ourselves, we're using the task. And as a result, we're going to be using the pool of threads. We certainly need the display result function, so let's go ahead and create that function. And this method, of course, says, what do you want to do? I don't want any result from him. And what should he take as a parameter? The price that I want to display, of course. And then, of course, once we come in here, we only solved one problem here. And what's the problem we solved? The problem of pool of threads. But the other problem is still with us, right? That you better be in the right thread. Otherwise, you're going to have a problem with updating the UI. So as a result, you still had to call the dispatcher invoke method and then set the content in the dispatcher. That problem didn't go away. You still have to deal with that complexity. So let's go ahead and run the code. And the only difference in this version compared to the previous version is that it is going to be in a pool of threads. The application is still responsive, but rather than we creating our own thread, we are just reusing the thread from the thread pool. That's all we are doing. Okay, that's great. We solved the problem partially here, but we still have the other problem. Now we have two more problems to deal with on our hand, right? And what are the problems? The first problem we have to deal with is you still have to contend with the context of threads. Am I in this other thread? Am I switching back to the UI thread to do the update operation? You still have to worry about that. The second problem you have to deal with is now you have two functions that you have separated this out. And as a result, while you're coding, you have to constantly keep in mind that you are doing the operation here in the UI thread, then launching a thread to run separately. You continue to do stuff, and when you're done with it, you got to call this other method, and then you have to start doing it. Now, you may say, in the simple case, it doesn't seem to be such a big deal, but imagine for a minute that I don't want to get stock price for just Microsoft. I want to get stock price for 20 stocks. Now I'm going to start 20 of these tasks because I can go to Yahoo and get the price simultaneously. But how do I then manage all these other methods like display result method? How do I know which one is for which? And the code tends to become quite messy as it goes along. And so the bottom line at this point is we have two problems. One is you have to still deal with the threading context that you have to deal with. And the second is the sequential code was simple and the concurrent code is so unnaturally different and far away from the simplicity that the sequential code offered. So it would be nice if we don't have to really be drastically that different. That is really where we want to go to. So let's get back to this and see what we can do. We used a pool of threads, but as we saw here, the sequential code and the concurrent code are quite drastically different, and we want to eliminate this kind of problems. So this is where .NET C# 5.0 really took from where it was left before in C# 4.0. So you are still using the task. You are still doing everything I showed you, except rather than you putting the effort to do it, you are telling, hello compiler, why don't you do that silly work so I can focus on my domain logic and get the coding done and go home. So in other words, whatever you saw just now, if that is a pattern of programming, and if that is what is expected that the code should be looking like, why do we have to write that pattern? Why can the compiler write that pattern, right? And what's the benefit of the compiler writing that pattern? Less work for us. We are more productive and less error prone because the machine does it automatically, whereas if you and I have to write that code, we could make mistake. Or even if we don't make a mistake, somebody else on the team could come back and make mistake. And every time somebody touches the code, there's an opportunity to make mistake. If the compiler generates this using a certain standard activity, we don't have to worry about that mess. So that is exactly what's going on in C# 5.0 with this async and await. So let's understand how this is going to work. So notice what I'm going to do here. I'm going to go back to this code, and in this code, I'm going to say, here's a ticker symbol I have on my hand. I'm going to ask the task to run, but the way I'm going to ask the task to run is to say, here I'm going to say a price equals, and this time I'm going to say task double and then dot run, and I call a run method on this. And when I call the run method, I specify to this guy the same thing I did before. So Yahoo Finance dot, and I'm going to give the price for him, and I'm going to ask him to use that. But in this case though, what is he going to do? The run method is going to run the code that I'm providing for him. So I provide the ticker for him, but the run method is going to return to me a task object. Well, rather than, so I could get the task object on my hand over here. But rather than doing that, what I'm going to do is simply remove all this code that we wrote. All this junk goes away. We'll get rid of this in a second because I need that code in a minute. I'll come back to it. But then I go back here and I say, I'm going to simply put this little word here called await. So essentially, rather than asking him to go run this task alone, I just put the await. Don't worry about the complaint he's making now. We'll come back to it. So I'm asking him to go await on the result. When he finishes the result, I'm going to say price label dot content equals, and I'm going to simply put the content update, which is this string and this value that I wanted to print. I'm going to just carry that over here and display the value right here at this point. So what did I do? Now, let's get rid of this part of the code. I don't need this anymore. Get rid of it. And you're looking at this and saying, wait a second, but you have solved one problem here, which is to use the pool of threads. Maybe you made this a little simpler by not splitting this code, but how does this really work? Well, first of all, what's happening in this case is, the minute you call await, it's a little whisper into the ears of the compiler. You went to the compiler and you whispered into his ears and said, hey, compiler, I want you to go do this another thread, by the way, and then whatever is remaining in this code, I want you to grab that piece of code, write another function like I did a few minutes ago, and go put that into that function for me. And so, in other words, rather than you having to write the separate method that you did a few minutes ago, you whispered into the compiler's ear, and the faithful compiler says, don't worry, I can do that for you. But this compiler is so cool, it says, as a bonus, I'll throw in one more thing for you. I will note down what thread you are on right now before I launch this thread. I'll go execute this stuff in the other thread, and before I call the method that I'm going to write for you, I will switch over to the contextual thread automatically, and then I will call your method. So as a result, you really simplified a lot of code. There is one disadvantage though. You need to learn how to read this code. The code no longer is what you see is what you get. What you get is a lot better than what you see, right? So what you see is this lines of code, but what you get is right as you hit the await method, you have another thread potentially running, and then whatever is after the await is going to run in a separate function, but it's going to run much later in your own thread, but after the thread that you called completes. Am I making sense? So there's quite a bit of compiler magic that's happening. It's a huge syntax shift. Now, of course, if you want to call await, they require that you mark this method as sync as well, just to communicate that your intent is very clear. That's what you meant. And notice as soon as you put the word sync, it was quiet like a well-fed baby, right? It was complaining a few minutes ago, but it's no longer complaining. That's all we did. So what does this really mean at this point? Let's go ahead and run this code and see if it produces the results we desire, and hopefully it doesn't crash and burn. So the application is responsive. We have sent the request, so that tells us that this is running in a separate thread at this moment, and I'm able to move things around. That tells me that the application is responsive at this time. But of course, when the response comes back is when we will know what's going to happen. Of course, you got to make sure it's in the right thread, because just because it didn't crash doesn't mean it doesn't have a problem, right? Remember, we talked about that before. But in this case, we trust that it's running in the correct thread. But we will verify that in a few minutes. So this has sent the request. It's running in a separate thread. The application is responsive. And then when the response comes back, it's going to update the content right here. And this part of the code, as you see here, is going to run in the UI thread. The request itself is running in a separate thread at this moment, and then the response is going to come back for us, and then we can get the display of the result. Okay, that's great so far. We could do that. But what is the, how do we know what thread these guys are running in? Because we do want to make sure that things are running in the proper thread. We don't want things to crash and burn and give us problems. How do we make sure of that? Well, in order to do this, what we can do is we can ask him to display the thread information for us so we can get a feel for this. Now, in order to make this a bit faster, what I'm going to do while at this is I'm going to simulate a response back so that we don't have to wait for this response from the service over and over. So I'm going to comment out this little code that's going to talk to the service itself. This is what it was doing the work so far. So I'm going to just go ahead and cancel that out for a second. And instead, what I'm going to do is simply return a random, actually let's go ahead and return 33.31 because that was the value was, right? But we'll cause a delay here. So thread.sleep, and just to delay this so we can actually see that it is actually taking some time. So I'll just give him a small delay over here for him to take time so we can actually see that it's responsive while we are still waiting on this. Great. So we gave a little delay over here. Let's go back and make sure this is working before we come back to look at the thread information. I gave a 2-second delay. The application's responsive. Notice after 2 seconds it displayed the result, so that tells us it's working. But what about the thread, by the way? So notice what I'm going to do now. I go back over here, and in the main thread, as soon as I click on the button, I'm going to say message box, and then I'm going to show the thread we are on. So let's go ahead and say thread.current thread, and let's go ahead and say current thread manage thread ID. So let's print the thread information. So this is printed right before I call the await. Within the await call, I'm going to go ahead and put a lambda expression right here. So this is going to become now a call to the return method. So it's going to be return that price. So we can return the value back. And of course, in this case, I want to display the thread we are on. So let's go ahead and do that. So I'm going to say message box dot show, and this is going to be thread dot current thread. And I'm going to say the method manage thread ID. So let's go ahead and print it. So thread.manageThreadID toString. And then, of course, when I come out of it, I want to display the thread one more time. So if I run this code this time, notice that when I click on the display, it says 1 because I'm in the main thread. That's a thread 1. I can click on this one more time. You can see it says 3 because I'm this other thread right now. And I click on OK now. 2-second delay later, it says 1 again because I'm back on the main thread now running. Go ahead, please. What if the button display itself is called from a non-event thread? How would it get called from the non-event thread? Find that guy and give him a slap, right? So it's a UI event. Yes. Correct. Right. So why can't that kind of code is not written by when you say it should do automatic switching, you're saying? Very simple answer. The more you ask it to do, the more you are paying the price in performance. And in 90% of the case, it is not required, right? The problem with managed services is when they start doing things that you don't care for, then it becomes annoying at the least and problematic at the best, right? At the worst. So the problem is that you can say I want all of these, but then every action has to be monitored and there are consequences to that. That's one of the reasons we all complain. Endlessly we complain. In almost every language I program in, I complain, oh, you guys don't take care of threading. But then I secretly say, but thanks anyways, right? Because if they do, there is other prices we have to pay. That is the consequence, right? So in an ideal world, we don't have to pay any price for anything and things work magically. But the reality is that we do pay price for things that come in and intercept. So that we have to be careful about. So we went ahead and wrote it this way. So this shows how the threading happens. So what's happening here? This means that the code that is behind has been executed in the main thread. So we saw the thread switching. But I want to emphasize one thing, by the way, before we go. Do not assume that what you saw happens all the time. In other words, just because you put async doesn't mean it's async. So read the word async as possibly asynchronous, not as asynchronous. So the word async means possibly asynchronous, potentially asynchronous. Let's understand what that means in just a few minutes. I'll show you an example of that. So having done this, we are creating a thread and we are calling the asynchronous code right here. That is great. We're able to call that into this other method. Now, if you look at this code, you can see that there are a few problems already, right? In this case, of course, we solved two problems actually. And the two problems we solved are, we didn't have to separate these two codes into two separate methods. We were able to kind of put them right next to each other. So you could say this code is almost close to the synchronous code we saw before, right? A little different, and it better be a little different because you need to know that it's asynchronous, but it's not drastically different, like you had to write multiple methods. Now, if you have to go ask for multiple prices, this method is going to be charmingly easy, right? How so? You can put a loop in there, and of course, in the loop, you're going to say, go get the price for this stock, await this, and that part will, of course, wait for the response to come back and run, but then you can go back and ask for another price and another price and another price. So all these requests will be lined up in other multiple threads, and when the responses come back, your code can start running. Oh, wait a minute, but what do I do about multiple threads, by the way, competing? Well, we almost kind of solved that problem without any effort because all those responses coming back will line up to run on the UI thread. So in other words, if I were doing this in other threads, I may have to worry about, oh my goodness, all these threads are coming back, I better handle concurrency. But the UI thread is the only thread that's going to run in this example, so that takes care of the concurrency problem because the responses are going to line up. So we don't have to worry about contention issues at this point. We can even find out which price stock is the highest price and then display that price at that time. So this is definitely a lot better in a lot of different ways. However, there is still one small problem. And the problem is, we took care of the control to do a synchronous call. Now imagine for a minute that you are writing code for multi-threading, and every time you talk to a service, you have to do task.run and create this thread, and then do the await on it, and then do the processing. And by the time you do this, about the 50th time, you would say, you know what, does it even make sense, by the way, to talk to a web service in the main thread? And it very rarely makes sense. So let's think about this for a minute. What kind of task, you earlier said you want to make the application responsive, and you are right. So a lot of times we use multiple threads to make the application responsive. But that's not the only reason, by the way. There are times you write multi-threaded code because you want the application to be faster, not just responsive. Now, for example, let's say that I want to send a request to 20 stock prices. If it takes about 2 seconds to get price for one stock, I don't want to spend 40 seconds to get a price for 20 stocks, because the user is going to get frustrated waiting for 40 seconds, right? So what is the, by the way, if you want an application to appear to be responsive, how fast should you respond? And don't say as fast as you can. That's not the right answer. 2 seconds, you said? By the way, the word 2 seconds is known in English as eternity. Right? You click on it, spin, oh my goodness, this is slow. So the human brain notices an activity after 250 milliseconds. So if I said something and I say really fast, and then you don't even know that I said it or I did something if I do it within 200 milliseconds. And that's one of the reasons why in your driving, and assuming that you do believe in safe driving, that is, you should keep at least a distance from the previous car. Why? The reason is at a given speed, your brain doesn't even know that the other guy hit the brakes for 250 milliseconds. So if you're too close, you don't even know that the other person hit the brake, and by the time you realize, you've already crashed into the car in front of you, right? So there's a reason why we use these kinds of metrics. Well, in the case of programs, it's the other way around. If you don't want the user to know that things are taking time, you don't want to keep the response for several seconds, because the user immediately gets, really angry at you. 10 seconds is enormous, right? I would say as soon as possible, but certainly you want to keep that 250 milliseconds in your mind, and once the user realizes they have done something, and the minute they realize, I'm not seeing a response, you want to at least give some response. But the other reason you want to do this to make this faster. Now imagine for a minute, if you have an application where your computation is very computation intensive, number crunching is what you're going to do. Now you may create a thread to make your code responsive, meaning you are going to move the application around, you don't want it to get stuck. So you would put this little computation in another thread. And somebody comes to you and says, you know what, this computation you're doing is in this one thread, but I can break this computation into smaller pieces, by the way, and you can run these smaller pieces in multiple threads. What is your answer? Yes or no? I'll give you a clue. It's only one of those two answers. Yes or no? You said yes. Then my next question is, how many threads should I create? Don't Google for it. That's not going to give you the answer. Right? Google, how many threads should I create? 42. Right? Well, the answer is no, by the way, if you are on a single processor. And the reason the answer is no is, your computation is computation intensive, right? Your task is computation intensive. If you give more threads to it on a single core, what is it going to do? Continuously context switch between these threads, and you're going to waste your effort. If you're a multi-core processor, if you're computation intensive, then the number of threads you want to give to this is equal to the number of cores you have, right? So you should never have more threads than the number of cores if your tasks are computation intensive. And of course, you just give one more for the application to be responsive, you're not going to gain speed by giving more threads to this, because they're going to be busy computing anyways. On the other hand, if the task you are creating is I/O intensive, meaning it has blocking, It has to wait for the disk to spin. It's got to wait for a network to respond. It's got to send a request to a web service. The answer is totally different. How many threads do I create? You want to create quite a number of threads if you have enough, a job to do. If you have a lot of jobs to do, split them up. But how many threads do I create? The number of threads you should create depends on what I want to call as a blocking factor. A blocking factor is the amount of time you're going to waste waiting for a response to come back. If my blocking factor is 90%, meaning in the time it takes me to do stuff, I spend 10% of the time doing work and 90% waiting for a response, then I want to create almost inversely proportional number of threads. It is number of cores divided by 1 minus the blocking factor, right? Now put this into perspective again. If the blocking factor is 0, meaning your task is computation intensive, number of threads is the number of core divided by 1 minus 0, which is the number of threads, cores itself. But if you have blocking factor which is higher than 0, you would divide by 1 minus that number, because it's a fraction. Your numerator is going to keep increasing, so that will be more number of threads compared to the number of cores you have. So you really have to know the blocking factor before you decide these things. But getting back to this, however, how do we deal with this? So you're saying, I got to do a lot of work here, but if my code is I/O blocked, it makes no sense to do this on my thread because I know it is going to get blocked. And as a result, it makes no sense for me to do this in the main thread. I would always do this asynchronously. In other words, don't push the burden on the user of your code. Take the burden on yourself so they can simply rely on the facility you provided. Am I making sense? So how do you do that? Well, to do this, what I'm going to do is to go back to this code, and rather than the task run and all those stuff we did here, let's go back to the code that we are using, the Yahoo Finance code. And what am I going to do here? I'm going to create yet another function right now. And this function is going to be called, it's going to return a double, but it's going to be called getPrice, and I'm going to call it async. So I just tagged along an async word so you know that it's going to be asynchronous. It takes a ticker as a parameter, and what I'm going to do within this, by the way, is I'm going to say I will take care of the problem here. So I called it async, right? And to make this work, I'm going to tag this as async. So I provide the async over here as well. And now in this code, I'm going to say, go ahead and create a task. Task double, in this case, dot run. And what am I going to run in here? Well, I'm going to run this symbol. I'm going to call getPrice, the non-async version, send the ticker to him, and whatever result he's going to return, I'm going to return it from here. Return a weight, and I'm going to say return that value back from here. So notice what we are doing in this particular example. What we are doing in this example is, we said, go ahead and put this into a separate thread, and then when the result comes back, await on the result and return it. Now for this to work properly, a little bit of a deal here, you say task double. Now this is a bit annoying when you look at it first, but you have to know what is really happening in this case. The function is returning a task, by the way, but the result it's going to return is going to be a double. So the compiler will wrap up the result that you provide into a task object and return it to the caller. It's complaining it doesn't know what a task is. Let's help the compiler deal with what a task is, and notice now it's no longer complaining. Again, to emphasize, your function will return a task, but what you return from the function is a double, and the compiler will rewrite your code to create a task object, put the result in there, and return. The benefit is you're not wasting code saying new task and put the result. That is done for you already. So quite a bit of compiler magic is happening again under the covers. So in other words, if I just want to return something here, I would have just said, for example, I would have just said return 33.21. This is perfectly fine, by the way. Notice the return type is task up here, but the return value is the type of the task. If you look at this, you would yell and say, oh my gosh, that's a compiler error. You are correct. if the word async was not here. But the fact that you put the word async is a whisper to the compiler to say, don't return what I tell you to return. Instead, wrap what I am returning into a task object and return it. That's what the word async in this context means. So now that you're returning this from this code, how am I going to use it? I go back to the code over here and I say price equals and simply await on the result, await, and this time I say and start get price async, and I'm going to say ticker symbol, by the way, dot text, and look at the beauty of this. I can get rid of that part of the code. I can get rid of that ticker symbol as well, because you are running this code in the main thread, and when you call the await, that's when it's going to go into the other thread. So this can be simply ticker symbol dot text. That's perfectly safe. You didn't need the other variable. So now that you await on this result back, you get the price back, and now you can display the result here, and then you can move on. So let's go ahead and run this example and see if it made any difference at all. So I go back and click on this. You're in thread 1. It went on and did the work over there. 2 seconds later, the response is back, and we displayed it. Now notice the beauty is it removed the burden from your shoulder. And you said, I'm going to await your response. Hey, async method, go run. But not only did it remove the burden from your shoulder, it opened up some really good possibilities. You left the other guy deal with multi-threading. That means it's less work for you, but you're also telling the other guy, I will let you decide what you should do. Whether you need a thread or not is your business, not mine. Let's see what the benefit of that is in a second. But before we go further with it, let's understand the threading here so we can actually make sense out of it. So to understand that, I'm going to change it to a string. That way we can know what the response, what thread he was running in, and we can display the result. So what am I going to do here? I'm going to say over here, var result equals, and I'm going to await the result from the other guy, from the other method we wrote. And now that I have the result back, I'm going to say return, and what am I returning? A string.format, and format is going to be the dollar of the result value, and then thread, and I'm going to specify what thread he is running in. So let's go ahead and say the result price, and then thread dot current thread. So current thread, and we're going to specify here the managed thread ID. ToString is not required in this case. So I'm going to return the thread information so that we can see where this code is running. So if I go back to this code and try to run this example one more time, we can see in this case, let me fix the error here. So manage thread ID, there we go. And so in this case, I'm clicking on this. The main thread is running in thread 1 one more time. As you can see in this case, it's running in thread 1. I click on this, the response comes back after 2 seconds. It is still 1 telling me I'm running in the main thread. But what thread did the code run in? That should be displayed in the text message that we displayed, isn't it? And notice it says 33.31 thread. It still says thread 1. Let's see why it says thread 1. Of course I know why it says thread 1, because I was stupid and sleepy when I was writing this code, right? So notice I looked at where the thread is, and I asked for that right here in this code. No, I don't want to know where the thread is from here, because remember, this is after await. So by mistake I did this, but it shows us something, right? This is running in, this is even better. So notice what's happening. You are in the main thread right now. And what did you do? You called await. You did not start a thread yet. You went into the getPrice method. And within the getPrice async method, you're still in the main thread. And then you called await. You're still in the main thread, but then you called run. That's when another thread is starting. So deep down, you are still in the UI thread, and now it starts the run method. That's going in another thread. When the response comes back, you are again back in the main thread. Logically makes sense. But of course, I really want to know what that other thread is, isn't it? So to do this, I'm going to go back to this code, and right here, I'm going to put a curly return over here for this. And then I'm going to close this here. Now I am in this other thread, so I can ask him to give me the detail right here. So I can say var other thread equals empty to begin with. And here I can say other thread equals, and we can ask him thread.current thread dot manage thread id.toString. So I got the other thread now. So now I can come back to this code and I can print out the other thread information because we stored it away, and I can say other thread. So this time we notice what the other thread is in the other thread, and then we come back and report it here. So let's go ahead and run this example one more time. So we are looking at this thing, click on this. One, it tells me you're in the main thread. Click it again. The response comes back. You should be still in the thread 1. Yes, you are. But notice that's thread 3 because that was the other thread that was running. So, all right. Now, by playing nice, you got some really good benefits on your hand. We relied on abstraction. And abstraction and encapsulation are good concepts. We know they are good, but how good can they be? The fact that you didn't take control of the thread and you said, I trust you to do the right thing because you are the one providing service. I'm going to just call you and wait on the response. Whether you create a thread or not is your problem. How you create a thread or not is your problem, not mine. So you lost a bit of a control. By losing control, you got a little bit better here. How so? First of all, it simplifies the caller, right? Your code is a lot simpler. And why is your code a lot simpler? And the reason why the code is a lot simpler here is that if you notice, this kind of fizzled into a very simple call. You simply said, await on the response. When the response comes, use it. So now notice, the only difference between synchronous code and asynchronous code is exactly 2 words. This word called await and this word called async over here, right? This, by the way, is only purely a convention. This is required. So in other words, this code almost is the same as synchronous code. Are you seeing it? Right? So if you remove the word await, this code becomes the synchronous code we saw before. You put the word await, it becomes the asynchronous code. Of course, the magic is under the covers, right? But to go from synchronous to asynchronous is just these 2 changes. To call the asynchronous version of the code rather than synchronous version of the code, and to put the word async in front of it. I'm sorry, await in front of it. That simple it is. But what is the benefit now? Notice the benefit. I want to run this one more time so you can keep this in mind. When I run this, main thread is thread 1, as you can see here. I click on this, the response is on thread 1 again, but the real code ran on thread 3. Keep that in mind, right? Okay, that's great so far. However, notice we just called await here, that's all we did. This can take advantage of some really exceptional thing. So let's go back to the code for a second. In the code, by the way, I've decided to do a little bit of optimization. And the optimization I'm going to make is the following. I'm going to say dictionary, and in this case, I'm going to say string comma double, and I'm going to say price cache. So I'm going to cache these prices over here equals new dictionary. So I have created a cache for myself. And then in my code down here, I'm going to say the other thread, that's perfectly fine, but I'm going to say if the price cache contains key, or it doesn't contain, the key is the ticker that I'm interested in. If it doesn't contain it, what do I want to do? Well, if it doesn't contain it, I'm going to do this job, right? So I'm going to go get the price in another thread, so I'm going to move this code in here. Well, but what if the price is in the cache? At the very end of this, of course, I'm going to say price cache ticker equals, and then the price we received, which is the result. But if it is already in the cache, I don't have to do this job. So I'm going to say thread dot current thread dot managed id dot toString. I'm going to just call that in the main thread itself, right? So I note the main thread's ID. If my cache is empty or my cache doesn't have the data I'm looking for, then I do this code in another thread and note down that thread. And then when I'm done with this eventually, I'm going to return from here. But what do I return? Not the result, because result is not available to me anymore. It's local to that little block. But I have price cache, and then I can say ticker. I can get it from my cache and return it. So benefit now. The benefit of doing this is, if I click on this the very first time, you can see that I'm in the main thread with the value 1 right now. I click on OK, it goes off and makes the request. I am displaying the result in thread 1, and the code executed in thread 3, just like it did a few minutes ago, no difference. But notice I'm clicking this display one more time. What happens? It is running this on the main thread this time, and I click on it, did you notice it came back a little quick, and it says the response in thread 1, but notice where it executed the code. In still thread 1. How so? It's because in the code here, you said await response from this, and when you went in here, you said, I am going to really look at the price value here. I'm going to ignore his timeouts, by the way. And so it's going to come in here, and it says, hey, look, I already have the value in the cache. I really don't have to call the other thread. And as a result, I can quickly give you the response right away because I have it on my hand, and I don't have to really switch threads at all. And so the entire code in the sequence runs in the main thread alone without having to context switch like I'm trying to do every time he says timeout, right? So basically the idea really is that you are really having a good flow here. You're not wasting performance switching threads. So going back to your earlier question, notice how they have optimized this to say we don't have to switch threads all the time when you call asynchronous. We can optimize this all the way down. And by the way, in agile development, we call this the last responsible moment, right? So in other words, you push it all the way down and say, okay, now we really have to do this work, and this is going to take time. Now is a great time to create a thread. So you're not prematurely optimizing it at your UI code level and say, oh, I got to call this, I better call a thread. You are walking along and passing down, and you're expecting, of course, there's a little caveat here, right? You expect the code below to do the right thing. And if the code below is not behaving properly and spinning its wheels for a long time, you will have problems, obviously. But assuming the code under the covers knows what it's doing and says, when you make this call, I will give this response quickly back to you if I can. Otherwise, I will call a thread and let that thread do the job. Then you have really optimized it, and your code got very simple. So if you now go back and look at how this code is going to look like after having done this, you can go back and remove all this cruff we wrote about thread information, get rid of that. And then go back here and say, I just want to return the result itself, not all of these, so we'll just change it to double again. And this time, of course, I simply return from here just the price cache itself and absolutely nothing else over here. So what does this really do in this case? Now we have simplified the code to the bare minimal at this point, and we are simply saying, go look for the cache, by the way. If the cache contains the price, just return the price. If the cache doesn't contain the price, go ahead and launch a thread at this point, because I got to wait for this web service, which is going to take time to respond. When the response comes back, by the way, so we could even get rid of these guys here, right? So this can be much simpler. We just say task.run at this point, and we can remove this portion, and we can simply say this is get price alone that we are asking at this point. And when he gives the get price value in the ticker, so we can simply say that's the value I'm expecting. So we simplified that code. And then here, of course, we store that into the cache, and then we are returning the cached value. So that code really came down to a very small amount of code. Going back to the other side of the code now, if you notice over here, what are we doing? We can get rid of these junk here, and we are saying go await on the get prices data, by the way, and when the data comes, just stick that into this value here, because that's where I want to display it. So going back and running this example, we got this working, we got a delay of 2 seconds, and then we have, of course, the result displayed back, and you can see how close this code is to the synchronous code. And of course, you are able to optimize on this as well. As you can see, first time I click on it, takes 2 seconds. Second time I click on it, it doesn't take 2 seconds at all, because we cached it. Of course, if I change the name to Google, for example, click on it, you're paying the 2-second price. Now you click on it, you're not paying the price because it's cached. So you can see how that's optimized, and that's what the await does. As a final note, by the way, if you're dealing with exception handling, that's fairly simple as well. Because all that you have to do in this case is simply put a try catch around this. And of course, when the response comes back, if the failure is on the server in the other thread side, your catch block will get triggered. But the catch block will be moved by the compiler to the other code where they implement the receiving end of it. But even when there's only a single thread involved, you still have these two methods, by the way, because the compiler doesn't know whether you're going to have another thread or not at this layer. So it will create those two methods. But the optimization happens because under the covers, it doesn't create this other thread. And that's the benefit you're seeing at this point. So you can see how this API, this improvement they have done in C# really simplifies, and the main goal really is this. You want to deal with concurrency, but you don't want to introduce errors in your code dealing with concurrency. You want this to be as natural as you can. And one of the goals is to really make the concurrent code and the sequential code as similar as possible. But we still have to keep some things in mind. You still have to make sure you don't collide with variables and start corrupting things, because then, of course, bugs get introduced. The disadvantage is, if you start mutating shared mutable variables, bad things can still happen. So concurrency errors are still a possibility. However, the effort to write the code has been greatly minimized by this approach. And so this really makes writing concurrent code more efficient